The European Space Agency's automated transfer vehicle has a crucial role in maintaining human spaceflight operations on the International Space Station, humanity's permanent outpost in space. Each ATV is named after a scientist or individual who fundamentally changed the way in which we understand the universe. And this series of films aims to examine these scientific breakthroughs and visionary concepts that made history. If one physicist had to be selected whose speculations have most transformed our understanding of the cosmos, it would be difficult not to choose Albert Einstein. Born in 1879 in the German town of Ulm, his work on the photoelectric effect won him the 1921 Nobel Prize for Physics and laid the framework for the quantum theory of matter. But it was his speculations on the nature of light, mass, gravity and time that forever changed humanity's view of nature. Einstein's name is most synonymous with the theories of special and general relativity. But what does relativity mean from a physics perspective? To understand the power of Einstein's insights, we must first explore the world as modelled by the Italian astronomer and physicist Galileo Galilei in 1632. Galileo was intrigued by how observations conducted by different experimental observers would be perceived by those observers. And it's the concept of different observers and their measurements that is central to relativity. Let's carry out an imaginary experiment, a thought experiment, in which a train is moving at a constant velocity. A scientist on board, we'll call him Observer 1, wants to measure the speed of an object moving in the train carriage. In his experiment, he rolls a ball along the floor and measures its speed from his perspective. The train carriage makes up what in physics terms we call an inertial or non-accelerating frame of reference. Now, imagine another observer, 2, who's standing alongside the train track in a different inertial frame. This observer is watching the experiment as the train carriage rolls by. Galileo reasoned that, from the stationary observer's perspective, the velocity of the rolling ball is easy to calculate. It's just the velocity of the ball as the train scientist measures it, added to the velocity of the train carriage with respect to the stationary observer. This is what Galileo thought of as relativity, and it implied that all motion in the universe was in relation to an absolute framework of space and time. Translating between different inertial frames was easy, just a matter of adding or subtracting relative velocities, and this tied in with most people's everyday experiences. In this Galilean relativity, although two observers might have different measurements for the speed of the ball relative to them, both observers would agree that the time interval that the ball took to cross the carriage was the same. Galilean relativity would suggest that different inertial observers would measure light travelling at different speeds, depending on their own relative velocities. Imagine a spaceship which has a laser on board. The laser fires a beam of light, which travels at 300,000 kilometres per second relative to the spaceship. Now, this spaceship is itself moving at 100,000 kilometers per second relative to another observer. Then surely that observer should measure the speed of the beam as being 400,000 kilometers per second. This is what Galilean relativity and common sense would imply. But it isn't what actually happens. In fact, both observers measure the speed of light as being the same 300,000 kilometers per second, regardless of their relative velocity. The speed of light in the universe is the same for all observers. Einstein realised that the only way to mathematically model this was to start with the observed constant speed of light and to change the way in which different inertial observers measure space and time. He needed to change, to make relative, that which Galilean relativity had made absolute, the relationship between space and time. Imagine we have a clock that works by firing a laser pulse across a set distance to a mirror. In this clock, each time the beam returns to the source, we have one tick. The clock operator sees the beam moving back and forth in a straight line in his frame of reference. Imagine that this laser clock is itself moving at high speed with respect to another observer. From this second observer's perspective, the path of the laser beam during each tick isn't a straight line. It's actually longer diagonal lines caused by the relative motion of the clock. And since light can only travel at this constant speed, the time interval for each tick on an apparent moving clock must be greater than the time interval for each tick on an apparent static clock. Einstein had broken the 3-century-old paradigm of absolute space and time in his new theory of special relativity, showing that the way we measure a time interval depends on our relative motion. From the point of view of a stationary observer, a clock that's moving seems to run slower than a clock that's stationary. And the faster the clock is moving relative to us, the more dramatic this relative time dilation actually becomes. Now, this seems contrary to all our everyday experience. My watch doesn't seem to lose time after I've run down the street. But the mathematics needed to derive the time dilation factor is a simple application of Pythagoras' principle to our laser pulse model. And what it shows is that the time dilation effect only really manifests itself at incredibly high relative velocities, those close to the speed of light. And when it does, the consequences are dramatic. Einstein's other great breakthrough, general relativity, which he published in 1915, owes its origins to an epiphany he had in 1907. Going back to the experiment I mentioned earlier of the train carriage moving at constant speed, Einstein realised that scientists conducting investigations in a constantly accelerating spaceship would get the same results as those they'd have if they'd conducted their experiments on a planet with a gravity field that produced the same acceleration. This is the equivalence principle. The effects of gravity fields are indistinguishable from the effects of acceleration. Why was this so revolutionary? Imagine we're in a spaceship, accelerating upwards. In the cabin, we fire a laser. Every second, our spaceship travels an increasing distance upwards because it's accelerating. So if we look at the effect this has on the beam of light as seen within the cabin, its path will appear to be curved, a parabola. And since the effects of gravity are indistinguishable from those of acceleration, Einstein realised that light, although massless, would curve in a gravity field. This theory was spectacularly confirmed by Sir Arthur Eddington during observations of a solar eclipse in May 1919. In fact, Einstein showed that all of the phenomena we traditionally associate with gravity fields could be replicated by instead thinking of how mass distorts the structure of space and time itself. Light follows not straight line paths, but the local curvature of space-time produced by the presence of mass. Einstein conducted another thought experiment in which light was fired upwards from Earth. The photons must, from the perspective of an observer higher in the gravity field, lose energy to climb higher, and they do so through a lengthening of their wavelength and a reduction in their measured frequency, a gravitational redshift. This implies that the same photon event will appear to have different wavelengths depending on the position of the observer in the gravity field. Imagine a laser located deep in the Earth's gravity field and fired upwards. This laser has a characteristic wavelength, frequency, and energy. From the perspective of our alien observer, however, at a higher position in the gravity field, the emitted photon will have its wavelength stretched by gravitational redshift as it climbs to a higher level, just like the wave on this rubber band. If the alien now points its laser downwards, as the alien's photons fall deeper into the gravity field towards Earth, their wavelength will be reduced and undergo gravitational blue shift. These effects have profound implications for our understanding of the effect of gravity on time. From the alien's perspective, the corresponding time interval for one wavelength, the period, is longer for the photon that climbed than for the photon produced at its level. But both photons were produced by exactly the same physical process. It's as if the alien's photon clock is running faster than the clock for the photon that originated deeper in the gravity field. Clocks, and therefore time, run slower the deeper you are in a gravity field, an effect predicted by Einstein in 1916 and finally confirmed experimentally in 1959 by Robert Pound and Glenn Rebka, who successfully measured this effect over a vertical height difference of 23 meters at Harvard University. The effect of gravity on time, combined with special relativity's time dilation due to relative velocity effect, has major implications for any users of GPS or SatNav satellite data. This includes the automatic rendezvous and docking systems on ESA's Automated Transfer Vehicle, or ATV. For ATV to successfully rendezvous with a moving target, the International Space Station, or ISS, it must be able to determine its own position continuously with incredible precision. A clock on a satellite orbiting the Earth is subject to two contrasting effects compared to one left on the ground. Special relativity, due to orbital velocity, would slow it down, while general relativity and increased distance from the Earth's gravity field centre would make it run faster. And for GPS satellites, orbiting 20,000 kilometres above the Earth's surface and with a velocity of nearly 4 kilometres per second, it's general relativity that dominates. The overall effect is tiny. Over one whole day, the clock difference between a GPS satellite in orbit and a ground observer will be less than 40 microseconds. But the effect is cumulative, and unless accounted and corrected for, this effect would render the whole basis of GPS navigation useless. ATV's GPS systems use software that constantly correct for the craft's altitude and velocity through the application of both special and general relativity, enabling the centimetre levels of positional accuracy necessary for a successful rendezvous between cargo ship and space station, whilst both are orbiting at nearly 8 kilometres per second. Each ATV docking is a superb example of how Einstein's theories of the nature of space, time and gravity successfully translate into operational reality for ESA's ISS programme.